Good afternoon. To continue with the discussion of last class, you can see this diagram, and I had told you to remember this diagram. The complete circle is the source entropy, and the complete circle at the right side is the destination entropy. And if these two circles are completely merging with each other, then that is a perfect communication. And if these two circles are not at all touching each other, then there is no communication at all. These are two extremes. Normally these two circles will merge with each other. The amount of merging, if it is more, then that the communication percentage also will be more. That way, the total entropy H of A comma B is called as joint entropy, and when the circles merge with each other, that merged portion or the overlapping portion is called as mutual information, and that is given the symbol I of A semicolon B. Now the remaining portion of the circle where there is no overlapping, that is called as equivocation, or it is also called as a conditional entropy. Now with this basic recap, let me continue further. I'll quickly go through these things which I had already covered in the last class. The term H of A comma B represents the joint entropy, which can be directly computed from the joint probability matrix. The term H of A minus H of A slash B represents the balance of information received at the receiver with respect to an observed output symbol. Hence, this difference is called as mutual information, and for the same equation is written as I of A semicolon B equals H of A minus H of A slash B. If H of A slash B equals 0, then the two circles will be of equal size and will overlap with each other fully as H of A equals H of B. Just a minute, students. Okay, there was some official interruption. Let me continue now. I of A semicolon B equals H of A minus H of A slash B. This is evident from the figure. Later on, we will be proving it mathematically also. So, in fact, all these results have to be mathematically proven. Only then we can write them diagrammatically. Because engineering is basically application of mathematics itself. So remember this, I of A semicolon B equals H of A minus H of A slash B. If H of A slash B equals 0, then the two circles will be of equal size and will overlap with each other fully as H of A equals H of B. This means that the channel is ideal. In such a case, H of B slash A equals 0 and I of A semicolon B equals H of A. On the other hand, if H of A slash B equals H of A, then the two circles will not overlap with each other at all, which means that the channel is completely noisy. In such a case, I of A semicolon B equals 0 and the two circles may or may not be of equal size. This I had told you in the last class that even if the source entropy is not communicated to the destination, still there can be a destination entropy which is purely because of the noise. That way, H of B need not be equal to H of A as well. H of B can be lesser also, H of B can be more also, because anyhow that is going to be equivalent to the noise. Now, continuing, the joint entropy H of A comma B can directly be computed from the JPM P of A comma B. But H of A slash B or H of B slash A cannot be computed from the channel matrices P P of A slash B or P of B slash A. The channel matrices contain only the conditional probabilities, right? This is because equivocation is dependent on joint probability as well as conditional probability. In the channel matrix, or it is also called as noise matrix, it is only the conditional probability that is available and the joint probability is not available. So for computing the equivocation, we have to have joint probability matrix. Hence for computing H of B slash A, both P of B slash A and P of A comma B have to be used. We need a conditional probability also, and we need the joint probability as well. We will see that in an example now. When H of A amount of information is being transmitted, an amount of information equivalent to H of A slash B is lost in the channel due to inter-symbol noise. Hence, the balance amount of information received at the receiver is called as mutual information. This we have already seen the definition. This is another way of defining mutual information. Here, when H of A is incident on the channel, H of A slash B is lost in the channel, and then only I of A semicolon B is received at the receiver. What is the meaning of inter-symbol noise? When symbols are being transmitted, in between two symbols, there can be noise. For example, I had given an example of ASK, FSK and PSK. Imagine a QPSK symbol is being transmitted, one waveform with the normal phase and with the 90-degree phase shift, 180-degree phase shift, 270-degree phase shift. Now in the QPSK modulation scheme, there are now these four symbols. It is the same waveform, same amplitude, same frequency, but with the different phases. So now this can contain 00, 01, 10, 11. The four symbols will represent actually 00, 01, 10, 11. That means each symbol or each waveform represents 2 bits of information. Now when these symbols or these waveforms are being transmitted from the transmitter, it is always a serial communication. So first symbol goes, next symbol goes. Now in between these two symbols, there can be a noise. That noise also can be a waveform of the same frequency, right? In fact, noise need not be a particular frequency. Noise can be right from 0 till infinity. Noise is not a predefined waveform as such, right? So when these symbols are being transmitted, in between them, if there is a waveform which is of the same frequency as that of the RF carrier, now that is coming in between the two symbols. That is called as inter-symbol noise. When you study digital communication in the next semester, you will come across one particular term called as ISI. ISI in the digital communication domain is called as inter-symbol interference. Now don't say that ISI is Indian Standards International. No, in our communication domain, it is inter-symbol interference. Between when these two symbols are transmitted, there can be a overlap of these two symbols in the frequency domain. And in the frequency domain, when these two can slightly overlap, that causes ISI, inter-symbol interference. You will study more about it in the next semester. Now here we call it as inter-symbol noise. Now because of the inter-symbol noise, part of the information can be lost. And whatever is the balance amount received, that is called mutual information. So by definition now, mutual information I of A semicolon B equals H of A minus H of A slash B. We can also write I of B semicolon A, that is also same as I of A semicolon B, because it is the amount of overlap between the two circles. That is H of B minus H of B slash A. Now as these both are equal, we can write it as H of A plus H of B slash A equals H of B plus H of A slash B. Now the LHS is nothing but H of A comma B, and the RHS is nothing but h of b comma a. Both are same. Now this h of a comma b or h of b comma a is called as a joint entropy, and as both are same, this is evident from the figure. Just a minute, I'll have to put a signature now. I'm pausing for a minute. Fine, let me continue now. H of a comma b equals h of b comma a, and this is evident from the figure. Means what? Joint entropy wise, whether it is source and destination together or destination source together, it does not matter much. Now let us try to prove whatever we had seen from the diagram mathematically. Now you may think, why should you prove mathematically? But as I told you, everything has to be actually proven mathematically. Later on we can represent it by means of the diagrams. So that way, we already know that h of a comma b equals h of a plus h of b slash a. This is by definition itself. Now let us substitute the actual expressions for h of a and h of b slash a. Now h of a is summation of I equals 1 to m of p of ai into Lg of 1 over p of ai. This is the source entropy. Now for the equivocation, by our definition, let us substitute it as summation of I equals 1 to m, summation of j equals 1 to m of p of bj comma ai and Lg of 1 over p of bj slash ai. This is based on the conditional probability and joint probability. You will have to recall the theorem of total probability as well as Bayes theorem, based on which we had defined equivocation. Now let us combine them. When we combine them, summation of I equals 1 to m p of ai into summation of j equals 1 to m p of bj slash ai into Lg of 1 over p of ai. This we can express this way also for the source entropy. And then plus summation of I equals 1 to m and summation of j equals 1 to m p of bj comma ai into Lg of 1 over p of bj slash ai. Now why did we put this particular term? Summation of j equals 1 to m of p of bj slash ai, that is going to be equal to unity, right? The sum of all the conditional probability is going to be equal to unity. Why? Because when ai is transmitted, it is sure that bj is received. That means when x1, x2, x3 are transmitted, it is sure that y1, y2, y3 are received. So the summation of all these conditional probabilities is going to be 1. That is why in place of 1, we are substituting this particular term, summation of j equals 1 to m of p of bj slash ai. Now let us use this expression further in this manner. Let me slightly reduce the zoom ratio. Okay. Now this is nothing but summation of I equals 1 to m of 1 to m into summation of j equals 1 to m p of ai comma bj. This is now a joint entropy, right? P of ai into p of bj slash ai is the joint entropy. P of ai comma bj into Lg of 1 over p of ai plus again below summation of I equals 1 to m, summation j equals 1 to m p of ai comma bj. Why? Because p of bj comma ai and p of ai comma bj both are one and the same. The joint probability wise both are going to be one and the same. That is how we got h of a comma b equals h of b comma a. So as far as the joint probability is concerned, they are equal. So we will substitute this term now. Now when we substitute this term, you can see that here summation of I equals 1 to m into summation of j equals 1 to m p of a comma bj is now common, and only these two terms are different. So we can put the common term here now. We put the common term, we got Lg of 1 over p of ai plus 1 Lg of 1 over p of bj slash ai, and we can write it in this manner, Lg of 1 over p of ai into p of bj slash ai. Now when we rewrite this complete expression, we get h of a comma b equals summation of I equals 1 to m into summation of j equals 1 to m p of a comma bj into Lg of 1 over p of ai comma bj, because this term is nothing but the joint probability. So that way now we obtain this particular expression for the joint entropy. Okay. Now this is the mathematical proof of joint entropy. So this indicates that h of a comma b can be directly computed from the joint probability matrix, because the JPM contains all these p of a comma bj. We can directly compute them using the joint probability matrix just by summation and this particular multiplication, which is based on the entropy itself. Hence it is always better that JPM is written first for computing the other entries. I have been telling you, whoever invented the matrix is a genius or was a genius. We don't know who. It may be one person, it may be many people, we don't know. It may be a team. Actually, I don't know. You may always search in Googleshwar and Googleshwar will tell you the answer. I have not yet searched till now. I feel today I should search, because in each class I should not keep saying that I don't know, I don't know. Let me find out today after the class is over. Anyway, instead of computing everything mathematically in this fashion using the equations, it is better that JPM is written, because we know the data of the probabilities with the source and the destination. Now when we write JPM, it is always better that we will compute all other entropies also. Now we will have one more derivation for the mutual information. This is again a mathematical proof of the mutual information. I of a semicolon b equals h of a minus h of a slash b by our definition. Now let us substitute for h of a, summation of I equals 1 to m of p of ai into Lg of 1 over p of ai. That is obvious. Let us substitute for h of a slash b minus summation of I equals 1 to m, summation of j equals 1 to m, p of ai comma bj, Lg of 1 over p of ai slash bj. Now summation of I equals 1 to m p of ai into Lg of 1 over p of ai into summation of j equals 1 to m of p of bj slash ai. We are substituting for unity as we had done in the previous derivation. Minus summation of I equals 1 to m, summation of j equals 1 to m, p of a comma bj, Lg of 1 over p of a slash bj. We have substituted this particular term as it equivalent to unity. So now summation of I equals 1 to m, summation of j equals 1 to m, p of ai comma bj. This we had obtained even in the previous expression. We will separate it out and we will have Lg of 1 over p of ai minus Lg of 1 over p of a slash bj. This we can write it as I of a semicolon b equals summation of I equals 1 to m, summation of j equals 1 to m, p of ai comma bj into Lg of p of ai slash bj divided by p of ai. When we get this particular logarithmic expression, we can write its composite expression in this manner. Now we have the mathematical expression for I of a semicolon b, or the mutual information. Again, this also can be obtained directly by using JPM. We don't have to use this expression for mathematically finding out the mutual information. So from the figure shown, just recall the figure once again, two circles, wherever it is overlapping, that is I of A semicolon B. You again visualize, left side is H of A slash B. Is it so? Even I am getting confused. Let me go back. Yeah, left side is H of A slash B, right side is H of B slash A, in between is I of A semicolon B, whole circle is H of A, right side whole circle is H of B, and the joint entropy is H of A comma B. You remember this once again. Now let me go back to wherever I was. From the figure shown, we can write H of A slash B equals H of A comma B minus H of B. We know that I of A semicolon B equals H of A minus H of A slash B. Mutual information equals H of A minus H of A slash B. This we know. Now, let us substitute this way. I of A semicolon B equals H of A minus H of A comma B plus H of B. Whatever is shown here, that let it be substituted for this term. Let me annotate. So, whatever is this term, that is substituted for this term now. So, now we have mutual information equals H of A minus H of A comma B plus H of B, or mutual information equals H of A plus H of B minus H of A comma B. This also is evident from the figure. The summation of the source entropy and the destination entropy minus the joint entropy is going to give us the mutual information. Now, always I used to say that Aliya Allah Maglaganda. Always it is not son-in-law, it is my daughter's husband. Same way, the same expression can be derived in so many other ways, and it is evident from the figure once again. If you remember the figure, you will remember all these formulae. Let us have an exercise now. For the given channel diagram, the channel diagram is given, calculate joint entropy, equivocation and mutual information, given that P of x1 equals 0.6, P of x2 equals 0.3, P of x3 equals 0.1. That means the source symbol probabilities is given. And in this diagram, this is now called as channel diagram. In this diagram, the conditional probabilities are also given. Means P of y1 slash x1 is given as half. P of y2 slash x1 is given as half. Naturally, P of y3 slash x1 is 0. Because half plus half is 1. There is no probability that when x1 is transmitted, y3 will be received. That is the characteristics of the channel. Now again, P of y2 slash x1 is half. P of y2 slash x2, sorry, P of y2 slash x2, let me discuss what now. P of y2 slash x1 I had already discussed now. Let me leave out x1. Coming to x2, P of y1 slash x2 is 1/4. P of y2 slash x2 is 3/4. P of y3 slash x2 is not there. Again, 1/4 plus 3/4 is 1. That means this channel has no probability of obtaining y3 when x2 is transmitted. So, P of y3 slash x2 is 0. Lastly, P of y1 slash x3 is not given. P of y2 slash x3 is half. P of y3 slash x3 is half. When P of y1 slash x3 is not given, it is 0. Because half plus half is 1. Now, this is a very straightforward channel diagram. Now, I will tell you, in the channel diagram, I can make a trick here when I give you questions. I may not give this at all. I may simply give this channel diagram. I may not give this at all. But in this channel diagram, you know that P of y3 slash x1 is not at all indicated. That means you can easily find out P of y2 slash x1 is P of y1 slash x1, 1 minus of that. You can find out this again. Similarly, imagine this I am not giving. Let us say P of y2 slash x2 I am not giving. I am only giving this P of y1 slash x2. But y3 slash x3 is not at all there. You can find out P of y2 slash x2 as 1 minus 1 over 4, straightforward. Similarly, I need not give you this also. You can directly find out P of y3 slash x3 is 1 minus half. That way, in the channel diagram, even if these three other probabilities are not given also, you can find out all the other missing probabilities. That way, we can actually slightly make these problems purposefully tricky so that you will find out the missing probabilities. So let me proceed now. Based on this, we will write the noise matrix now. Say half, half, 0, 1/4, 3/4, 0, 0, half, half. That is evident from the channel diagram. This you can easily write. Once you write the noise matrix, you can easily write the JPM also. Why? Because this is given now. 0.6, 0.3, 0.1 is given. Using the data of the source probabilities, source symbol probabilities, we can now write the JPM. You can see this. JPM is nothing but half into 0.6, half into 0.6, 0. Because the first row is for x1. Let me zoom in. You can see now, right? See, P of x1 is 0.6. First row is corresponding to 0.6 and we have half, half, 0. So, half into 0.6, half into 0.6, 0. The conditional probability into the source symbol probability is going to be the joint probability as per our definition. Coming to x2, 1/4 into 0.3, 3/4 into 0.3 because x2 is 0.3, lastly 0. Coming to x3, the first element is 0, next element is half into 0.1, next half into 0.1, half into 0.1 and half into 0.1. That way we have JPM now. Now this JPM we have this value. Let me zoom out now so that you can clearly see this. Now I have this P of x comma y, 0.3, 0.30, 0.75, 0.2250, 0.05, 0.05. Once I obtained JPM, I can find out everything now from this JPM. Let me find out the joint entropy h of x comma y just by using all these data given in the JPM. 2 into 0.3 LG of 1 over 0.3, 0.3, 0.3 twice they are there, 0.05, 0.05 twice they are there. So that way it is 2 into 0.05 LG of 1 over 0.05, remaining is 0.75, 0.225. When we do the summation of all of that, we get 2.2391 bits per symbol. This is the joint entropy now. Okay. From the JPM, we can find out P of y1, right? Using the JPM by doing the totaling of the column values, column entries, we can find out the destination symbol probabilities as well. So you can see here, P of y1 is 0.3 plus 0.075. P of y2 is 0.3 plus 0.225 plus 0.05. And P of y3 is 0.05. You can verify this again here. See, 0.3 plus 0.3 is 0.6, that is P of x1. And 0.075 plus 0.225 is 0.3, that is P of x2. And 0.05 plus 0.05 is 0.1, that is P of x3. That way, when you add the row elements, you will get the probability of the source symbol. When you add the column elements, you will get the probability of destination symbols. So you will get P of y1, P of y2, P of y3. Now that is this. P of y1 we get 0.375, P of y2 we get 0.575, P of y3 we get 0.05. We can find out the destination entropy now. H of y is using all these probabilities of received symbols. We can apply our classical expression to get h of y equals 1.2059 bits per symbol. Now we can find out h of x using the source symbol probabilities, that is 1.2955 bits per symbol. Now let me zoom in. Now you have h of x comma y, you have h of y, you have h of x, right? You have the source entropy, you have the destination entropy, you have the joint entropy. Now you can easily find out the equivocation. Just remember that picture or diagram. You can find out the equivocation whether at the left side or at the right side. You add both of them, h of x plus h of y, add both of them and subtract h of x comma y. What you will get? You will get mutual information, right? H of x plus h of y minus h of x comma y, you will get I of a semicolon b. You will get mutual information. Once you get mutual information, h of x minus mutual information is h of x slash y. H of y minus mutual information is h of y slash x. That way you can find out the equivocation. Now let me zoom out. So now equivocation, this way also can be found out directly using the expression. You can go through the method which I followed just by remembering the diagram, or you can find out this way also. H of x slash y is h of x comma y minus h of y. That is also evident from the diagram only, right? H of x comma y is the joint entropy minus h of y, because there is an overlap between h of x and h of y. The remaining portion is h of x slash y. You will get 1.0332 bits per symbol. Now mutual information is given by I of x comma y equals h of x minus h of x slash y. That is 0.2623 bits per symbol. Now we have obtained these values, whatever was asked. You can actually obtain all other values whichever are required. You can verify all the expressions with reference to the diagram. So now look at this. What is the conclusion? Let me tell you the conclusion before going to the note. What is the conclusion here? Just look at the values and tell me the conclusion. See, h of x is 1.2955 bits per symbol. H of y is 1.2059 bits per symbol. But I of x comma y, x semicolon y is 0.2623 bits per symbol. Now can anyone unmute and tell me what is the conclusion for this exercise? I'll annotate this way. See, this is what we obtained as destination entropy. This is what we obtained as source entropy. This is what we obtained as mutual information. Now my question is, what is the conclusion now? Can anyone unmute and tell me the answer? Or can you put the conclusion in the chat box? Okay. Harshita has put the information as the percentage of information is 20.3%. Very good. She immediately calculated the percentage of information. Okay. So this means, see, out of 1.2955 bits per symbol information that is present at the source, the destination received only 0.2623 bits per symbol. That means out of this much, only this much was received. Even though at the destination, that is 1.2059 bits per symbol, if you subtract this 0.2623 from 1.2059, whatever is the remaining at destination is because of noise itself. That information was not from the source. And 1.2955 minus 0.263, that much of information is lost in the channel. That itself is that h of x slash y. That itself is the equivocation from the source side that is lost. Now you have to understand the importance of the Bayes theorem. Using Bayes theorem and using the theorem of total probability, we are right now finding out the information content that is actually received at the destination. Now that is how mathematics is going to be applied into information theory. In fact, when mathematicians deduce all these results, they will not be knowing that it will be used later on by someone else. But someone else who are into some other domain, when they study the mathematical findings, then they will have an idea to use them for those particular applications. For example, when George Boole wrote the Boolean algebra, at that time, transistor was not invented at all. When George Boole wrote the Boolean algebra before 1940s, transistor was invented in 1947. BJT was invented in 1947 exactly. And later on, people started using it in the digital logic circuitry, and integrated circuits started coming out after 1960s. There was nearly about 20 years of gap where nobody thought that this Boolean algebra will be useful as such. They were thinking using only these two, 0 and 1, with the binary mathematics, who will use this? But George Boole had an idea at that time. He framed all those laws, and using that, now we can express logical equations for a NAND gate, a NOR gate, AND gate, OR gate, NOT gate, XOR gate, XNOR gate using Boolean algebra. That is how the use of mathematics is going to happen in engineering and in technology and in science. Okay. Let me proceed now. Let me zoom out again. So the conclusion, as I've already told you, is the channel noise is going to come in between source and destination. Let us see the note now. Note 1. Similarly, h of y slash x also can be calculated as h of y slash x equals h of y minus I of x semicolon y. You need not memorize all these equations. You just remember the diagram. That's it. You remember the diagram. You will write all these equations on your own. That's it. But the derivations which I showed you, those two derivations you will have to write and practice. Because we are going to ask these derivations in the test also, in the exam also. Now that is part of our evaluation. Ultimately, students should have some written form of evaluation. Only when you write, then you will remember. That is one reason. Second reason is, only when you write, you will understand the complications of those derivations. Third reason is, only when you write those derivations, in future, you can also derive some other equations. I should tell you my one small experience. I was writing an article for a journal paper, for an international journal paper, for my PhD's work. And at that time, I had to derive an equation for the operating frequency or the working frequency of the ring oscillator. So when I was deriving for the ring oscillator, I had to characterize the ring oscillator in terms of the CMOS inverter. Connecting 3 inverters, we will get one ring oscillator of stage 3. Minimum stage is 3 there. It is always an odd number for the normal ring oscillator. So now I will have to characterize these 3 inverters in the form of their MOSFETs. Now I have to characterize the MOSFETs in the operating regions of saturation region and linear region, right? Because an inverter is actually going to work in three regions: cutoff, active, cutoff, linear, and saturation. Now, in case of a ring oscillator, it will never going to cut off because the signal is going to come back again and again. So the inverter is going to operate only in these two regions, in the linear region as well as in the saturation region. Now, using the device equations of the MOSFET for the saturation region as well as the linear region, I had to characterize the inverter. Now, using the inverter's characterization, I had to characterize the ring oscillator. Finally, obtained an expression for the operating frequency or the working frequency of the ring oscillator, and I presented in a conference the same work I improvised for a differential ring oscillator, and now it is published in one Springer journal as well. The earlier work was also published in one reputed Scopus indexed journal. So how this was all possible? It was possible because I had written down the device equations for the MOSFETs so many times, and I had remembered all those equations, and I used all those equations for the derivation of the ring oscillator's expression. That is how we engineers are going to apply the principles of mathematics only for our usage in the engineering designs. That is why we will have to ask you these derivations even in the test and even in the exam. Only when you write something, you will have a double registration into your memory, and only when you write something, then only you will appreciate the person who derived that particular equation. Otherwise, just think about the applications of engineering science and how is it possible just by reading and understanding without writing. So writing is part of learning as well. Okay. Anyway, but when you remember the diagram, you will remember all these equations. But the two derivations which I showed you earlier, you will have to write it and practice it again and again and again. Lastly, the second note, the equivocations can be calculated directly also using the respective expressions and probabilities using P of AI, Bj and P of AI slash Bj are made use of. But the effort becomes laborious. Instead of using that diagram and instead of using the simpler expressions, just like they say, no, instead of directly eating, have your food or morsel of food in the right hand and bring your right hand below the neck and bring the hand all the way from the left side to your mouth and try eating it. Why should I have that much of pain? We can directly consume the food, right? But sometimes there are some crazy people, for a simple thing also, they will put a bigger effort, sometimes just to show off also. But that is not required. The equivocations can be calculated directly also using the respective expressions and probabilities, where the joint probability and the conditional probability are made use of, but the effort becomes laborious. Instead, we can remember the diagram and we can use the simpler expressions. Okay, but when it is automated, now when all these processes are automated, when we are using a computer for the expressions, then we cannot say to the computer that remember the diagram and use these equations. We cannot, right? So in such a case, we will have to write the actual expression using these probabilities either in C language or in C++ or in MATLAB or even in Verilog also or in VHDL also. We will have to write the actual expression using the probabilities, and then using a program, we will have to use a particular software for that. There we cannot say that as per the diagram, remember the diagram. Machine cannot remember the diagram. We human beings can remember the diagram. So effort will not become laborious for the machine. For the machine, it is nothing there. It is within a fraction of a milliseconds, fraction of a second, or maybe in milliseconds and microseconds, it will compute the answer. Fine, let me end the class for today. See you in the next class. to discuss more interesting things about information theory. Until then, take care and goodbye.